Hello everyone, my name is Kiran Choudhary and I am your botany faculty at Infinity Learn by Sri Chaitanya. My lovely students, let us start this session, and before starting, let me tell you I am here and starting a very fresh series, that is Chak De series, students. So let us Chak De NEET 2022. Students, it's a kind request. Till now, if you haven't subscribed to Infinity Learn, do consider subscribing to Infinity Learn YouTube channel and do not forget to hit the bell icon. Very, very important, so that you may not miss any session in future, right? So do not forget to hit the bell icon and also do consider giving me a thumbs up. Next, yes, as I told you, I am here. We all at Infinity Learn are here with a very new series, Chak De series, right? So students, in today's session, I am going to discuss what? I am going to continue transport in plant chapter. Remember, I started chapter number 11 of your 11th class biology textbook. Chapter name is Transport in Plant, and the topic that we are going to do in today's session is I am going to continue plant-water relationship. So remember what I have already explained you on this topic, plant-water relationship. So water potential, right, and osmosis, these are the two very important topics that I have already covered. Now I am going to continue with another left out topics under plant-water relationship. So in this class, first of all, I will talk about what? First of all, I will talk about osmotic pressure. Yeah. Second, I will talk about, students, the next topic is actually plasmolysis according to your NCERT textbook, but rather directly jumping into the topic of plasmolysis, rather I will discuss the three types of solutions, right? Hypotonic, hypotonic and isotonic solution. After completing all the three types of solutions, then I will try to explain you what will be the fate of a plant cell when it is placed in different types of solutions. So instead of studying separately the solution and separately the fate, what I am going to do is I am going to club both these things, right? So we will directly start with fate of a plant cell in various types of a solution, and in that I will simultaneously explain the type of solution as well as the fate, and in that only I will cover plasmolysis also. So plasmolysis is the topic according to your NCERT, but I am not taking the heading plasmolysis because I am going to take the detailed discussion of all three types of solution, and under hypotonic solution I am going to explain plasmolysis. Okay, so do not get confused, and please note this thing, students, each and every line and word of your NCERT is going to be covered in this class. I can guarantee you this. So after taking the entire lecture, I request you open your NCERT book and try to read each and every line from the para, right? And you will realize that yes, each and every word and concept was very smoothly covered during the lecture. So this is something you got to do. Okay, so second thing what we will do is fate of plant cell in different solutions. Next what I will teach you, students, is next what we need to understand is imbibition. Very important, right? And before jumping into the osmotic pressure topic, I would love to solve those important in-text questions that NCERT has mentioned just after the discussion of osmosis. Remember, in the previous lecture I told you that in the coming one I will discuss them, right? So this is what from I am going to start the lecture. So the very first thing that we will do is in-text questions. Let us start session with important questions. All these questions are given in your NCERT. So let us try to understand what are the answers and how to get there. And secondly, then we will jump into the topic of osmotic pressure. So here it goes, my kids. What we need to understand is these questions, right? So these are the various in-text questions, and before reading out the question, you need to understand what this question is in relation to what. So please pay attention over here, students. First, this is what I am explaining you, the prerequisite knowledge to solve this, right? The condition, the given condition also. So the given condition is, this is chamber A, this is chamber B. Please note, students, this is chamber A, this is chamber B, and here is what? Here is the selectively permeable membrane, right? Now what you need to understand is, in this chamber A and chamber B, two things are present, water and solute. So both chamber A and chamber B has solution in it. Chamber A has less amount of solute and chamber B has a greater amount of solute. I hope this much is clear to all of you. So these particles that you can see over here are representing to what, my kids? They all are actually representing to solute particles, right? And see, here water is more and solute is less. Here solute is more and water is less. So before trying to solve these questions, my kids, you need to understand the given situation, and secondly, you need to interpret what all conditions are given over here. So first I will help you to understand what all situation is given and what we can interpret, and then we can jump into the questions. So let us try to understand this. So as you can see here, number of solute particles is less and solvent is more. And also note one more important thing, students. I am going to represent the solute concentration. Please note this, I am going to represent solute concentration by this sign and solvent concentration by this sign. So please remember these important notations. I am going to use small s under brackets solute concentration and capital S under brackets for solvent concentration. So yes, let us try to apply this here. As you can see, the solute particles is actually less. That means in chamber A, the solute concentration, we need to define 2-3 things. Solute concentration, we need to define solvent concentration, we need to define free water molecules, and then we need to define water potential. These are the important things we need to do here also. Solute concentration, solvent concentration, free water molecules, the number of free water molecules, and water potential. So I'll write water potential A and water potential B so that it becomes easy for us to understand. Now very simple, with the help of this diagram you can easily come to know, since here these purple, or right now I have circled them with red color, these molecules are actually lesser in chamber A. So that means the solute concentration in A is actually less, right? And here it is less, but here it is more. Now you can see, in comparison to water, if I talk about here, water molecules is actually more and water molecules in the chamber B is less, because you can see more blue portion over here and less blue portion over here. So the solvent concentration is actually more in chamber A and solvent is actually less in chamber B. Now students, remember, try to recollect what I explained you when I was teaching you the effect of solute on water potential. Just in case if you are still not familiar with water potential or osmotic potential, pressure potential, osmosis, I request you to check out the botany playlist and see. In the end you might find, most probably in the end only you will find all those important lectures I have taken on water potential relations. So that's my request if you are still struggling. Anyways, I'm going to explain this in short here also. So see over here, students, whenever the solute particles are more, so effect of solute particle is what? They will actually decrease the free water molecules number. How? Very simple. If you if you have, for example, right now this is a beaker and here you have pure water, pure solvent in it, that means all water molecules are free to move. Now what you do is, in this beaker you add some solute in it. What will happen? By adding solute in a pure solvent, what will happen? The solute, for example, is NaCl. Na and Cl will go and dissociate, right? Na is going to have a positive sign, Cl will have a negative sign. And remember, water molecules are polar in nature. They have partial positive and partial negative charge, right? So the polar water molecules will try to bound with the positive and negative charges or positive or negative ions, right, present in the water when you have added the solute in it. So what I want to say, let us conclude. Listen this very clearly, students. Whenever you add solute in a pure solvent, the total number of free water molecules actually decreases, because some of the water molecules now get bonded with the ions or solute particles. So whenever in a pure solvent you will add solute in it, there will be decrease in the free water molecules number. Why? Because now after adding solute, some of the free water molecules will go and bound to the ions or solute particles present in the solution. So if particles are bonded, or if water molecules are bonded to the solute particles, that means they are now not free to easily move from one place to another. And that is why addition of solute has, remember I have told you, I have explained this very nicely in the previous class, that how addition of solute has a negative effect on the water potential, because it increases the total number of free water molecules available for movement. I hope this much is clear, right? So free water molecules available in chamber A will definitely going to be more, and here it will be less. Why here it will be less? Because some of the water molecules has now bonded with the solute particles, and here the total number of water molecules that has bonded with the solute particles will be less, because solute concentration is less. Very simple logic. Yes. Next, water potential. As you know, students, the total number of water potential depends upon the total number of free water molecules, right? It doesn't depend upon straight concentration of the water molecules. Rather, water potential depends upon how many water molecules are actually free to move, right? So the total number of free water molecules actually shows or reflects on water potential of any given solution. So since this chamber A has a higher number of free water molecules, that means its water potential will be high, and this B has greater concentration of solute, so free water molecules available in it will be less, and hence water potential of B will be less. So this is what you needed to understand. Yes, it's a very good question, students, and you need to understand it conceptually. Only then you'll be able to give answer, and you'll be able to retain the concept as well, right? So you don't have to mug up the answer. Let us try to understand in a very simple way how to get to these answers. So this is the prerequisite knowledge that you must have before jumping into the question. Just in case you are not familiar with any single term or not clear with anything, do let me know in the chat box. I would love to address your doubts. Now let us see the questions, right? I really hope you are able to see the question, but in case you are not, let me know. I will definitely read out the questions for you. The first question is, solution of which chamber has a lower water potential? Tell me, so which chamber, A or B, has lower water potential? We have already done our homework. We know that water potential of chamber B is actually less because it has fewer or lower number of free water molecules, because it has higher concentration of solute. So it will be chamber B. Simple. Solution of which chamber has a lower solute potential? Remember, students, this is a previous concept I have taught you in previous this class, right? So previous to previous class you need to see for this, but just in case, but obviously I am going to explain the concept here also, but not in that big detail. So even if you are struggling on it, do check out that lecture. So solute potential, very simple, students. The concept is, Please note all this in your NCRT, straight in your NCRT. Hello Ankita. Hello. And I will really appreciate, Ankita, if you will participate in giving answers. Okay, so the concept is, please note this in your NCRT. More is the solute, comma, less is the psi s. What is psi s? Solute potential. So the concept is more is the solute, less is the psi s. So it is asking solution which chamber has a lower solute potential. Who will have lower solute potential? The one which is going to have more solute, because lower psi s will be there in a chamber which has more solute. So more is the solute, lower or less is the psi s or solute potential. So very simple. Who has more or greater amount of solute? Simply chamber B. So answer will be B. Please students note this concept in your NCRT textbook. Yes, very right, Ankita. Next is, in which direction will osmosis occur? Very simple. Osmosis occurs where, students, let me tell you, water movement. Remember this, very important. Water movement. With respect to water movement, what you need to understand, water always moves from a region of high water potential to a region of lower water potential. Please note this. Water always moves from a region of higher water potential to a region of lower water potential. Water always moves from a region of higher water potential to a region of lower water potential. Please note this point over here, and same thing you need to apply here. So in which direction osmosis will occur? Osmosis means movement of water, diffusion of water across a selectively permeable membrane, obviously, right? So movement will be from region of, or a chamber which is at higher water potential to a region which is at lower water potential. So see here, osmosis will occur in which direction? Who is at higher water potential? Chamber A. And who is at lower water potential? Chamber B. So water is going to move in this direction from chamber A to B. From chamber A to B. Yeah, next question. Which solution has a higher solute potential? So see students, B and D are actually just opposite to each other. Here it is asking about lower solute potential, and here it is asking about higher solute potential. So obviously answer is going to be opposite, but let me explain the concept also. Higher solute potential, see, more is the solute, less is the psi s, right? So lower is the solute, higher will be the psi s, just opposite, more solute, less psi. More is the solute, less is the psi s, right? So if lower is the solute, more will be the psi s, and that's exactly what is asking. Which solution or chamber will have higher solute potential? The one which is having lower solute concentration. Who is having lower solute concentration? C. Chamber A has a lower solute concentration. So answer is B, will be A. Clear? Hello Abhirami. Good afternoon. चलिए आगे देखते हैं. At equilibrium, which chamber will have lower water potential? So please remember this very important concept, students. This flow of water from a region of high water potential to a region of lower water potential will continue only and only till equilibrium is attained. So at equilibrium, both the chambers will have almost equal value of water potential, and at that point of time the water molecules moving from chamber A to B and from B to A will be almost equal. Hence there will be no net flow of water between the two chambers at equilibrium. So at equilibrium, water potential of A will be almost equal to water potential of B. So both will be at equal water potential, and hence there will be no net movement between these two chambers. So I really hope students this much is crystal clear to all of you. Now let us see the next question. If one chamber has water potential of -2000 Pascal and other has minus 1000 Pascal, which is the chamber that has the higher water potential. Very simple. Tell me, from minus 2000 and minus 1000, which one has the higher water potential? Anyone? Whenever, see students, yeah, very simple, just the simple maths you need to use. Very simple maths you need to use. So whenever minus sign is in front of a number, it is going to decrease its value, right? So whenever minus sign is there, you need to consider the number, lower number, the one which has higher value. So in comparison to minus 2000 and minus 1000, which is going to have hold higher value? Minus 1000. So minus 1000 is at higher water potential. So minus 1000 is a bigger number than minus 2000. Minus actually reduces the value of the number, right? So the chamber which has minus 1000 value of water potential will be at higher water potential value. Last question students, then we can conclude this much. What will be the direction of movement of water when the two solutions are at water potential 0.2 and 0.1? Now see, very important that you need to understand. Yes, very right. How about letting me know your name, because I am unable to understand your name. The one who has given answer minus 1000, Doc. So how should I pronounce your name? Should I say Doc? So please let me know your name. That will be really easy for me to pronounce your name. So right now I'll call you Doc. Okay. So next thing is, yeah. So one solution, one chamber has a water potential 0.2 and another hand 0.1. So see students, this is a good, like a little tricky thing. What you need to understand is, in question F and in question G, almost same thing is asked, but what the NCERT has played with little bit of maths. It's not little bit of biology or concept they are playing. They're just playing with, yeah, they are just playing with the number, right? So in question F, both the chamber had water potential value in minus. And when it comes to question number G, both the chambers are having water potential values in positive. Yes, that is what you need to understand. So whenever the number of water potential is in positive, right, that means simply you need to go with the number which has the higher value. So in 0.2 and 0.1, who has higher water potential? Definitely 0.2 is bigger than 0.1. So the movement or the direction of water movement will be, the water will move from a chamber which has 0.2 value of water potential to a chamber which has a value of 0.1 water potential. So just remember, when there is negative sign, go with the lower number. When there is positive sign, go with the higher number. So in negative sign, the number that has the lower number with negative sign, the lower number will be at higher water potential, and with positive value, the number higher value is going to be at higher water potential. I hope this much is clear to all of you. Now let me know if there is any doubt in the chat box. Next question. What we need to do? We are done with this question students. I really hope now after this class you will never ever get confused in all the concepts and all the questions, right? Why and how to get these answers. So it is a very good exercise. You must try this in text question. Now next what we need to do is we need to start osmotic pressure. The next topic that we need to deal in this class is osmotic pressure. So let us see what osmotic pressure means. So here it goes. Osmotic pressure. So before explaining you the definition of osmotic pressure, I would love to explain you what is happening in this image, right? This is your NCERT image, and you need to understand this. Only then you can understand the definition of osmotic pressure. Definition of osmotic pressure is not given directly, rather it is mentioned indirectly, right? So something that you need to understand indirectly, you need to understand from where it came. Only then you will be able to understand this. Yes, this is what osmotic pressure means. So first of all, I will explain this diagram and then we will proceed further. And now in this diagram also, this is condition A and this is condition B. So what I want you to, after this situation, this will come. So right now I am not going to compare these two figures, rather what I will do is I will focus on this one and then I will explain the B part. So it is my kind request to all of you that please stay focused on this one and then I will start explaining this. So let us start with this one. So in this, what is happening? Let us see what is happening here. So see my kids, here this is what? This is a beaker. Yeah, this is a beaker and in a beaker there is a water. There is a water. Let us consider it is a pure water, right? Although it is not mentioned, let us consider it as a pure water. And then there is a funnel inside it. What is this? There is a funnel inside it. The funnel, the opening of the funnel is actually closed or covered with the help of a membrane. With the help of a membrane, right? Now, see here students, inside the funnel, what is enclosed? Sucrose solution is enclosed. So in this apparatus, there is a beaker in which there is water, there is a funnel in which there is a sucrose solution and there is a membrane over here. Now you already know students that water has the tendency to move from a region of higher water potential to a lower water potential, and that's exactly what we need to understand here. So let us define the water potential values over here. So what is this? Let me talk about this funnel first, right? Let us talk about the solution. Let us talk about the solution that is present in the funnel. So here the solute concentration is actually high and solvent concentration is actually low, right? You know why this is happening, my kids? You must be familiar now because I have already explained you this thing. Solute concentration, solvent concentration. So solute is actually higher in a sucrose solution and solvent is low. Now remember students, whenever you are saying something is high and something is low, that means higher and lower are relative terms. If I am calling that solute is greater in funnel and solvent is lower in concentration in funnel, that means I am relating to something. What exactly am I relating to? To the surrounding. And who's there in the surrounding? Water is there in the surrounding. So see students, this is a beaker and in this beaker, you remember there is water. So in comparison to the water that is present in the surrounding, right, the solution inside a funnel has a higher concentration of solute and a lower concentration of solvent, right? That means the free water molecules, just give me a moment. Yeah. So the free water molecules in funnel or in solution also I can write, or in solution will be what? In solution it will be low. The free water molecules in solution will be less and free water molecules will be higher where? Free water molecules will be higher here. So in short, now what I can say is water potential of solution, right, and comparing to the water potential of the beaker, So how can you say this water potential of the beaker is more? Water potential of the beaker is more, or you can say water present in the beaker has a higher water potential value in comparison to the water that is present inside the solution, and that is true also because in beaker there is no solute and in the funnel there is solute, and presence of solute is going to have a negative effect on the water potential value. And you already know water कहाँ से कहाँ move करता है? Water moves from a region of higher water potential to a region of lower water potential. So tell me, who is at higher water potential? The water that is present in the beaker is at a higher water potential, and the water that is present in the funnel is at lower water potential. Hence, there will be movement of water inside the funnel, right? So after some time, you can experience there is increase in the level of the solution inside the funnel due to osmotic entry of water inside the funnel from the surrounding environment. I hope this much is clear. So why did I explain you all this much? So that you can be in a comfortable zone and you can understand that why water is diffusing inside the funnel instead of coming outside the funnel, because both these two questions can come in your brain, that why water is entering, why can't water come out? Water will not come out as of now when there is a difference in water potential value. The water which is present in the beaker is at higher water potential value, and the water that is present in the solution in the funnel is at lower water potential value, and we already know water moves from a region of higher water potential to a region of lower water potential. Hence, water will move inside the funnel, and after some time you can see increase in the level of the solution inside a funnel. Now there is something that you need to understand, students, is कब तक चलेगा ये, at what time, right? Till what time this increase in the level of the solution inside funnel will take place? It will take place until the equilibrium is established. What is equilibrium? Equilibrium is a point, students, where the free water molecules in the beaker and free water molecules present in the funnel will be almost equal. That means at equilibrium, water potential of the solution inside the funnel and water potential of the water inside the beaker will become almost equal. So when there is no difference of water potential, hence there will be no net movement of water, right? So that's all I wanted to explain. Now let us move to the next portion here. Please try to understand, students. What happens is when this, now we are not talking about equilibrium right now. Now let us come back and let us come a place or a position where equilibrium is yet not attained in this solution. So let us consider a situation where still the water is diffusing inside the funnel, right, and equilibrium is not attained. So at that particular point of time, what will happen? At that particular point of time, if you apply an external pressure, and you keep on applying it until and unless the very last water molecule stop diffusing inside the funnel, that's the value of that pressure is known as osmotic pressure. I repeat myself. So in this situation, when water is diffusing inside the funnel, right, diffusing inside the funnel because of the difference in water potential value, right? So at that time, if you start applying pressure externally on the funnel, and what are you doing? You are actually applying the pressure in just opposite direction. Water is trying to enter into the funnel, right? And you are trying to apply pressure from upside. So you are trying or applying pressure in just opposite direction to the entry of the water. So you keep on applying pressure on the funnel, and up to a certain value of this external pressure, when you see that now no more water molecules are getting or inside or entering inside the funnel, that particular value of pressure is known as osmotic pressure. So I really hope, students, now you will be understanding that why the definition of osmotic pressure is given in such way indirectly it is given that what is osmotic pressure? The pressure required to prevent water from diffusing, right, from diffusing inside the funnel. So please try to understand, this is how osmotic pressure is defined in an indirect manner, right? And that is why, to make you comfortable with the definition of osmotic pressure, I did this whole explanation. I really hope students you found this explanation quite helpful and easy for your understanding. So that's what I wanted to explain about osmotic pressure. Now I will introduce the definition of osmotic pressure with all of you. So yeah, so what we will do is, let me reduce this so that I can write. Let me write the definition for you now. Definition of osmotic pressure, right? Definition of osmotic pressure. So what is osmotic pressure? It is the pressure required to prevent water from diffusing, See, so what is osmotic pressure? It is the pressure required to prevent the entry of water or diffusion of water into the solution. So pressure required to prevent water from diffusing in. So if you will go on applying water externally on the funnel at a certain value of the external pressure, you can see now no more water molecules are entering or diffusing inside the funnel, and that's the value of the osmotic pressure. Now let us try to understand some more important points related to osmotic pressure. So here it goes. Another important point that you need to understand is osmotic pressure is a function of solute. So it is a function of solute concentration. So what do I mean by that? What do I mean by that? Very simple. So more is the concentration of the solute, inside the funnel, more will be the osmotic pressure, or more will be the pressure required to prevent water from diffusing. I repeat myself, students. Osmotic pressure is a function of solute concentration. That means if solute will be more inside the solution, where is the solution? Inside the funnel. So inside funnel, if concentration or the solute particles are greater in number, more will be the pressure required to prevent water molecules from diffusing it. Why so? Because not to forget, students, water actually moves according to the concentration gradient, right? Diffusion of water, osmosis of water, all depends upon the concentration gradient, right, of the water potential, right? So if the gradient of water potential is higher or larger in value, water molecules will diffuse inside the funnel with a greater speed and in larger amount. I repeat myself, when there is greater amount of solute in the solution, more water molecules with higher speed will try to enter into the solution, and hence more amount of water will be required to prevent their movement or diffusion inside it. Yes, so that's how solute concentration, that's how osmotic pressure is a function of solute concentration. Very, very important. More is the solute concentration in a solution, more will be the osmotic pressure required to prevent water from diffusing in, because it is this value, this higher or increased value of solute, which is going to create a greater gradient or difference in the water potential of the two regions, right? And hence more water will diffuse. Next point that you need to understand is, I am explaining the same point in words over here. So, more is the solute, greater will be the pressure or osmotic pressure required. So, more is the solute, greater will be the osmotic pressure. Next, what you need to understand over here is, my kids, next what you need to understand over here is, next is osmotic pressure is actually, students, yeah. So, one more important thing, how do you define osmotic pressure? Osmotic pressure is denoted by pi. So, pi is actually equals to minus psi s. Yes, very important. Minus psi s. So, this is something that you need to understand over here. Very important for everybody. Very important for everybody. तो देखिएगा स्टूडेंट्स, ये बहुत ज़्यादा important है आप लोगों के लिए, and you need to understand this very nicely. See this. So, pi equals to minus psi s, and what is pi? Pi is the osmotic pressure. That means osmotic pressure and solute potentials are actually equal in number, but just opposite in sign. Very important conclusion this is. I request everybody to note this. I request everybody to note this. Pi equals to minus psi s. That means numerically pi or osmotic pressure is equal to solute potential but opposite in sign. Now note one more thing students, if you realize a solute potential is generally expressed in negative value. So, if you put negative in front of psi s, that means you are trying to make this pi value a positive value, and that is true also, because osmotic pressure or pi is the positive pressure that you apply on the funnel in order to prevent the entry of the water molecule. So, please note students, osmotic pressure is the positive pressure. Osmotic pressure is the positive pressure. So, these are the very important thing that I wanted you to understand. All these important points I really hope now are crystal clear to all of you. Just in case if any point is not clear, do let me know in the chat box students. Do let me know in the chat box. So, okay, so now we can continue with another important topic that we need to understand. So, another important topic that we need to understand is, now let us see Till now what we have covered, students, we have solved all the important in-text questions related to osmosis and we have understood the osmotic pressure too. Now let us see what will be the fate, what will be the fate of a plant cell when it is placed in different types of solution, so, right? And in this only, students, I will explain you whenever a plant cell is placed in a hypotonic solution, why it undergo plasmolysis. So the plasmolysis topic will be covered in this section only. So let us start and try to understand all important facts over here. So let us start with the very first one, and that is hypertonic solution. Let us understand what is first hypertonic solution, and then I will explain you. Remember, as I told you, I will explain what a solution is and what will be the fate of a plant cell simultaneously. Now before I start explaining you, one more thing that you need to understand is, students, this hypo, hyper and iso, all these important terms are actually relative in nature. That means you cannot say something is hyper until and unless in the surrounding something is hypo. You cannot call something as hypo if something in the surrounding is hyper. So whenever you are calling a solution as a hypertonic solution, something in the surrounding should be hypo also. So please understand, all these terms hyper, hypo, iso, all are relative in nature. They cannot be used isolatedly for any individual object, right? So let us try to understand what is a hypertonic solution, and here I will take solution as well as a plant cell togetherly. So here it goes, my kids. So here I am drawing a solution. So as of now, you need to understand this is a solution, right? So although you must be thinking there's a boundary over here, but try to understand this is a solution. This is a chamber, right? This is a chamber where it has solution in it. Now, next thing that you need to understand over here is, I have to draw a plant cell in it. So here it comes a plant cell. So this is how a plant cell will look like. So let me do what? Let me draw one more in it. So you know it is a plant cell, and a plant cell is going to have cell wall outside, and inside to it there will be cell membrane. So I am trying to draw a double membrane structure. Over here. So yeah, this is how it will look like. So let me align it properly for you. Yeah, this should work good for us. Okay, so now let me write it, what I want to explain here. So this is your hypertonic solution. So this is your hypertonic solution, and this is our plant cell. Also, whenever you say a solution is hypertonic solution, that means you are referring to a concentrated solution, right? A concentrated solution. Now always remember one more thing, students, the concentration term is by default used for solute. So you are saying the solution is concentrated, that means it has a higher amount of solute in it. I will emphasize on it a little later also. Now let us try to compare the condition inside this hypertonic solution. Let me write it for you also in case you forget. This is hypertonic solution, right? So a hypertonic solution is what a solution? A solution in which concentration of solute is higher in comparison to what? Higher in comparison to the surrounding. who is there in the surrounding? Plant cell is there in the surrounding. And not to forget students, a plant cell can also act as a solution, because inside a plant cell there is cytoplasm, there is vacuole. So vacuole is enriched in solutes, right? So solutes present in the vacuole are responsible for producing the solute potential that I have already explained you in one of my previous lecture, right? So understand students, water is available in the cytoplasm and solute is there in the cytoplasm as well as in the vacuole also. So in a way, plant cell also act as a solution. So when I am calling the surrounding solution as a hypertonic solution, that simply means the amount of the solute will be higher in this external solution in comparison to what is there inside the plant cell. So here I will define 5 terms. With respect to hypotonic solution and plant cell, I will define 5 terms. Solute concentration, solvent concentration, free water molecules number, water potential values and comparative one, and the osmotic pressure. All the 5 terms are extremely important to you. Why? Because all the 5 terms have been discussed again and again in your NCERT wherever the fate of a plant cell in iso, hyper and hypotonic solution are mentioned. So I want after this class everybody should be in a comfortable zone where you do not struggle on the words that why this term is applicable here or that there. So why solute concentration is more inside a plant and less in a solution? Why osmotic pressure is more here and less there? So I want everybody to be clear on those lines, and hence we are doing this homework over here. So see students, first I will do what? I will define solute concentration. Remember, smallest solute concentration. Then I will define solvent concentration, capital S, solvent concentration. Then we will define the free water molecules, right? Next, what we need to understand is water potential values, and then we will see what, my kids, then we will see actually osmotic pressure. Remember, pi, osmotic pressure of the solution. So I am writing solution also in the below this, okay. Next, let us define all these things or all these terms here also for the plant cell. So solute concentration, solvent concentration, free water molecules number, then water potential of cell, then I can write osmotic pressure of the cell. Now let us start comparing it. So please note here students, right now what am I going to do? Right now I will actually help you in understanding what hypotonic solution is, and then when a plant cell is placed inside a hypertonic solution, how it will react or respond. So let us see the values first. So as the name suggests, it is a hypertonic solution. Hypertonic means highly concentrated. That means solute concentration is higher with respect to whatever is there in the surrounding. Who is there in the surrounding? Plant cell is there in the surrounding. So here the solute concentration is higher. Hence, the solute concentration in the plant cell will be lower because you have mentioned the solution is hypertonic, relative term. If this is hyper, this has to be hypo. Next, solvent. So you already know students, when there is higher concentration of solute, obviously the solvent will be lower, right? So higher is the solute, solvent will be less. Here also solvent will what? More. Why? Because the solute concentration is less. Inside a plant cell, solute is less. That means solvent will be more. Remember, all these are relative terms. So solvent concentration in the external surrounding hypertonic solution is less. Hence, it will be more inside a plant cell. Now, let us talk about the status of free water molecules, my kids. Very simple. See, I have been repeating it multiple times. What you need to understand is, whenever there is solute concentration, right? So presence of solute is going to decrease the free water molecules available. Hence, more will be the solute concentration, lower will be the available free water molecules for diffusion. Simple. So the section or the chamber or the part inside this diagram which is going to have higher solute concentration will have lower free water molecules number. So here in the surrounding hypotonic solution, the solute concentration is more, and hence the free water molecules will be less, because some of the free water molecules now got bonded to the solute particles, right, and hence they are not freely available to move now. Here the solute concentration is less, hence the available free water molecules are more. Right? Let me know, students, you people are comfortable with these terms or not. I am trying to super simplify all the important terms that are mentioned in your plasmolysis topic, and if you understand, if you listen each and every word patiently with all your attention, I can guarantee you, you will never ever in the future struggle in any word or term in the entire plant-water relationship topic, right? Next, you know, students, whenever free water molecules has a direct impact on water potential, so, right? So more is the available free water molecules, more will be the water potential. Less is the available free water molecules, less will be the water potential. Because why? Because, my kids, it is the free water molecules only that is going to move. So if a region has a higher concentration of free water molecules, that means it is a higher water potential. A region which has fewer or lower number of free water molecules, it will be at lower water potential value. And you already know water moves from higher water potential to lower water potential values. So water potential here will be low. Why? Because of the low or fewer number of water molecules, and here water potential of the cell will be higher because of more number of freely available water molecules. Now what you need to understand is, let us talk about pi, my kids. What is pi? Pi is the osmotic pressure, and not to forget, my kid, I have already told you right now, before this explanation I was teaching you osmotic pressure, and there I told you solute concentration, right? So osmotic pressure is a function of solute concentration. More will be the solute concentration, more will be the osmotic pressure. And see over here, my kids, see this. Osmotic pressure is a function of solute concentration. Osmotic pressure is the function of solute concentration. That means more is the solute concentration, greater will be the osmotic pressure. Hence the osmotic pressure of the solution will be greater than or higher than the osmotic pressure of the cell. Remember, osmotic pressure is a function of solute concentration. More is the solute, more is the pi. Less is the solute, less is the pi. Simple? Okay. Now, this is what you need to understand. Now, let us conclude this by writing the movement of water. So, you already know, students, water will move from a region of higher water potential to a region of lower water potential. Right, kids? Yeah. So water will move from a region of higher water potential to a region of lower water potential. So from this diagram, you should be clear that exactly, yes, exactly where do you think water potential is higher? It is in the cell. And where the water potential is low? Outside the cell. So water will move, water will actually come outside. Water will actually come outside the cell. Water will actually come outside the cell. Water will come outside the cell. Water will come outside the cell. So why water is moving outside the cell? Because water present inside the cell is at higher water potential in comparison to the water molecules that is present in the surrounding solution. So as a result, what we can conclude, my kids, that water will keep on coming outside, until the equilibrium is established. right? But see students, if this water continues to come, at a certain point, you can see the cell has actually become plasmolized. Remember, in your NCRT, this beautiful diagram is mentioned. See this diagram. So whenever a cell is actually placed inside a hypertonic solution, water comes out and cell undergo plasmolysis process. And this is how a plasmolysed cell look like. Now we are done with all important terms that are mentioned in your NCRT with respect to hypotonic solution. So what are we going to do now? Now let us see the observations. So what is the observations we see with respect to the plant cell? So the observations are what are the observations? Very simple. You can see the observations here, my kids. Very simple. First observation is plasmolysis will take place. Plasmolysis means the cell will become plasmolysed when water will come out. Okay, yeah, exosmosis, Ankita, very right. When water comes out of the cell, it is known as exosmosis. When water enters inside the cell, it is endosmosis. Very right. Next, plasmolysis will take place. That is, in that also students, it is given in your NCRT. First, the water will come out from the cytoplasm and then from the vacuole. So during plasmolysis, first water will come out from cytoplasm and then from the vacuole. Next observation is students, the protoplast. The protoplast, you can see the protoplast will shrink away from the cell wall. Yes. So after continuation of this exosmosis, the plant cell will reach to a place where the entire protoplast of the plant cell will get somewhat shrink from the surrounding cell wall. So somewhat like this in the end stage of plasmolysis, you can see a plant cell. I can show you here rather. So if this is what a cell is, then it will start getting detached from the cell wall. So this is what? This is the cell wall, and this is what? I think it should not be visible to you at that much. So let me change the ink. This is the cell wall. And this is the protoplast. So see students, what happens finally? Protoplast starts getting detached from the cell wall. So that's all you need to understand under the topic of hypertonic solution. And please note students, here I have not only explained to you what is a hypertonic solution, but with that I also explained to you, my kids, what will be the fate of a plant cell when it is placed inside a hypertonic solution. Please note, whenever a plant cell is placed in a hypertonic solution, it will undergo plasmolysis and protoplast will shrink away from the cell wall. So that's all from this section. So I think we are good to switch now to the next portion. So let us see what we need to understand next over here. But before that, let me take a small water break. okay, and then I will continue. You can also take water break. Doubt? Is there any doubt? Let me know. Okay, so fine. So let us see now the next point. What do we have to understand next is hypertonic solution. Sorry, let us see, students, the next that you need to understand is a hypotonic solution. We have already done our understanding explanation on hypertonic solution, where we saw if a plant cell is kept in a hypertonic solution, it will undergo plasmolysis. Now let us see what is a hypertonic solution. Again, my kids, we are going to do the same exercise. Okay, so the exercise begins over here. This is our solution. Please consider this as a solution. Next we need to draw a plant cell. Next we need to draw a plant cell. This is a plant cell. Let me draw two lines for you so that you can understand it is a plant cell. One representing to the wall and one line representing to the membrane or the protoplast. Okay, so I think this will do good. Let me give a green color to the protoplast. Yeah, perfect. We are good to start now. Let me fit this protoplast inside this cell wall. Okay, this much space would be enough for us to understand. Yeah. So see, my kids, let us do the same exercise what we have been doing. What is a hypotonic solution? Hypotonic solution is a dilute solution. It is a dilute solution. That means here the solute concentration will be lower in comparison to the surrounding. What is there in the surrounding? Plant cell is there in the surrounding. So if I am calling this solution as a hypotonic solution, that simply means that this solution will have lower solute concentration in comparison to the solution that is there inside the plant cell. Let me write here for you, plant cell. This is a plant cell. Now let us do the same work, the same homework. We will define all the 5 important terms, right? All given in your NCERT. Solute concentration, solvent concentration, free water molecules number, water potential, and then osmotic pressure. So here it goes, students. We need to understand the solute concentration, solvent concentration, free water molecules number, and then what are we going to do is water potential comparison, and then I'm writing solution also here, and water potential, osmotic pressure of the solution. Similarly here also solute concentration, solvent concentration, free water molecules, water potential of the cell, and osmotic pressure of the cell. Now let us do the comparison. Very simple. So see, as the name suggests, the name is hypotonic solution, a dilute solution. That means the solute concentration will be lower in comparison to the solution which is there in the surrounding. Who is there in the surrounding? Plant cell is there in the surrounding. So here the concentration of the solute will be lower in comparison to who is there in the surrounding? The plant cell. So in this situation, student, the solute concentration of the surrounding hypotonic solution is less and of the plant cell more. Please note this very important difference. Now, as the name suggests, if solute concentration is less, that means the solvent concentration will be more. Differently, because solute concentration and solvent concentration inside a solution are also relative. In a solution, if the solute is high, then solvent will be low. If solvent is low, solute will. So it's very simple. Both these are what? These are simply the relative values. Solute concentration, solvent concentration within a solution are relative value. If in a solution the solute concentration is more, that means solvent will be less. Very simple. Hello Dia. So let us see. Let me know Dia if you are unable to follow anywhere. So chaliye. So here the solvent concentration is more. That means here the solvent concentration will be less, and it has to be. See, if you consider plant cell as a solution, if solute concentration is higher, definitely the solvent concentration will be low, right? So all this is going to be opposite only. Next, free water molecules number. Yes, very simple. We have been doing this. Wherever there is higher value or concentration of solute particles, the free water molecules number will go down. Solute concentration is more, free water molecule number goes down, right? Because some of the freely available water molecule will go and bound with the solute particles, right? And hence, if the water molecules are bounding to the solute particles, that means they are now not free enough to show any kind of movement. Hence, those bounded water molecules, that got bound to the solute particles will not play any role in deciding the water potential of that particular solution, right? Hence, the free water molecules is going to be higher in the hypotonic solution in comparison to the free water molecules that are present inside a plant cell. Why? Because plant cell has greater concentration of solute, that means it has lower free water molecules available for diffusion or osmosis. Next is water potential. Very simple. Free water molecules has a direct impact on water potential value. More is the free water molecules number available. I repeat myself. More are the free water molecules available in the solution, more will be its water potential value. Lower the number of free water molecules available in a solution, lower will be its water potential value. Direct relation. So, free water molecules number is higher in hypotonic solution, hence its water potential will be higher. Hence, its water potential in the solution will be less because it has lower free water molecules number. Now, my kids, we need to talk about osmotic pressure, and you know, my kids, osmotic pressure is a function of solute concentration. Pretty simple. Yeah, enough of drawing I have done. Now see, so osmotic pressure is the function of solute concentration. I have already explained you. More is the solute concentration, more is the osmotic pressure. Lower is the solute concentration, lower will be the osmotic pressure. See, here the solute concentration in hypotonic solution is less, hence its osmotic pressure of the solution will be less. Less in comparison to what? Less in comparison to the solution that is there in a plant cell. In a plant cell, my kids, see, the solute concentration is higher, hence the pi or osmotic pressure value will also be higher. So, please note this very important conclusion, my kids. Lower is the solute concentration, lower is the osmotic pressure. Higher is the solute concentration, higher will be the osmotic pressure. Clear? Hello, dear. Yeah. So all my kids, are you able to understand whatever I am teaching you? Please let me know. Is there anything you want me to repeat? Feel free to ask. How about Dia letting me know how she is feeling inside the lecture? How are you feeling? Are you able to feel these concepts now more clearly? Let me know in the chat box. Okay, so my kids, we already know that water moves from a region of higher water potential to a region of lower water potential. This is something I have been repeating multiple times, right? So see here kids, water moves from a region of higher water potential to a region of lower water potential. Now tell me, who is at higher water potential over here? So see students, yes, hypotonic solution is at higher water potential in comparison to the solution that is there inside a plant cell. So the water that is there in hypotonic solution, it is at higher water potential value in comparison to the water that is present inside a plant cell. So water will do what? Water will actually enter inside this cell from the external surrounding hypotonic solution, right? Water everywhere will enter inside the cell, and as a result my kids, you can see there will be increase in this portion. So cell will start swelling up. Cell will start swelling up. Why? Because of the osmotic entry of water inside it. And hence in your NCERT it is also given, yeah. So this is the diagram that NCERT has given for a plant cell that is kept inside a hypotonic solution. So see my kids, whenever a plant cell is kept inside a hypotonic solution, there will be osmotic entry inside the plant cell, and because of which its cytoplasm will expand and the cell will actually increase in size, and hence you can say this particular cell will be termed as turgid cell. So turgid cell, when you get a turgid cell, whenever a plant cell is kept inside a hypotonic solution, there will be entry of water molecules inside it from the surrounding hypotonic solution, and as a result the cell will swell up and will be termed as turgid cell, right? I hope this much is clear to all of you. Now let us write what? Now let us write some observations. Now let us write some important observations. Let us write some important observations. Yeah, so observation number 1. So what did you observe, my kids? What did you observe? You observed that there will be entry of water inside the cell. So this is your first observation. Your first observation is entry of water inside plant cell. First observation. Second observation, as a result of entry of water inside the cell, cell will swell up. Cell will become turgid. Cell will swell up. Swelling of cell. Swelling of plant cell. Next point. Now see students, please understand this. Due to osmotic entry of water inside this plant cell, there will be cytoplasmic expansion. Definitely cytoplasm will expand because of the entry of water inside it. So due to the osmotic entry of water inside a plant cell, there will be cytoplasmic expansion, and this expanding cytoplasm will develop another type of pressure known as turgor pressure. So there will be development of TP. What is TP, my kids? You must be familiar. It's a turgor pressure. Next that you need to understand is, students, this development of TP, this increasing of TP, the increased amount of osmotic entry. So as the water molecules is going to continuously enter inside a plant cell, there will be continuous increase in the value of TP, that is the turgor pressure. Now this increased TP is going to increase the free energy of the system. Which system? The plant cell. I repeat myself, students, this developed TP inside a plant cell and this increasing TP inside a plant cell is going to increase the free energy of this plant cell. Hence, there will be development of pressure potential inside the cell. So, there will be development of psi P. What is psi P? The pressure potential. What is psi P? Pressure potential. Next thing, students. Next is, this TP is ultimately responsible for extension and elongation growth inside a plant, right? So TP will be ultimately responsible for extension and elongation growth of a plant cell. Right, my kids? Now students, I hope this much is clear that when a plant cell is kept inside a hypotonic solution, water will enter inside the plant cell will swell up. There will osmotic entry of water inside a plant cell will leads to cytoplasmic expansion. Cytoplasmic expansion will develop TP. Increased TP is going to increase the free energy of the cell, right? Free energy of the water that is present inside the cell. Hence, there will be development of the pressure potential inside the cell as well. Next, this TP is ultimately responsible for extension and elongation growth inside what? Inside the plant cell. Yes, Ankita, you're right. In this case, endosmosis is taking place because water is moving inside the plant cell from the surrounding hypotonic solution. Now, another important thing that you need to understand is, students, on the previous slide, what did I explain you? On the previous slide, I explained you about the hypotonic solution. So remember, students, what happens in a hypotonic solution? The cell is plasmolysed. The cell undergo plasmolysis, but this plasmolysis process is usually reversible. It is usually reversible. It is usually reversible. Why am I saying it is usually reversible? So remember, students, if a freshly plasmolysed cell, a cell that was placed in a hypotonic solution. So if a freshly plasmolysed cell is placed in a hypotonic solution, then the situation of plasmolysis can be reversed. The cell will start gaining inside the water molecules that it has lost when it was placed in the hypertonic solution. Hence, plasmolysis is usually, remember, usually, please notice this point also, students. Plasmolysis is usually reversible. So when you keep a plasmolysed cell in a hypotonic solution, in a dilute solution, it may regain its shape again because of the entry or endosmosis of water inside it, right? I hope this much is clear. Now we are good to go. Yeah, so all this is what I wanted to explain you about hypotonic solution. Let me know if there is something you are still not clear with. I would love to repeat it for you. So that's all from hypotonic solution. Remember kids, we understood what is a hypotonic solution, and we also understood what will be a fate of plant cell, or how a plant cell will respond when it is placed inside a hypotonic solution. Remember, it will become turgid. Now, the last thing that we need to understand in this section is what? It is the isotonic solution. Now, let us see what is an isotonic solution. The same exercise we need to do again. The same exercise we need to do again. Okay, so I think you must be enjoying now this exercise, right my kids? Yeah, so this is what your isotonic solution, and this is what? This is your plant cell. I need to draw your plant cell. This is your plant cell. In plant cell, let this be the boundary. So we can create another one. We can change, like, let me give an orange color, sorry. Let me give an orange color to your wall and a green color to your membrane. It is just simply my preference. Okay, so now let me fit it properly for you. Yeah, pretty close, I guess. Okay, so I think we can start our discussion from this point. So what is an isotonic solution? Let me write it for you. So this is your isotonic solution, right? And this is your plant cell, right my kids? Isotonic solution, and this is your plant cell. Hello Rohit, very warm welcome in this class. I am explaining isotonic solution right now. Okay, so let us see what is isotonic solution. Now students, to understand this, very simple. Isotonic solution is that solution in which the solute concentration is equal with respect to the surrounding environment, right? So for example, if this is a solution and in surrounding there's a plant cell, and if I'm calling this solution as is an isotonic solution, that means solute concentration in this and solute concentration inside plant cell is almost equal. This is an isotonic solution. So let us do a nice comparison of both these over here. Let us do a nice comparison of both these here. So I will do what? I will do a good comparison over here. Let me draw this outside only. Yeah, so see here. Okay, this is good, I guess. So here what I'm going to write my kids, here I will write about cell, and here I will write about the solution. I will write about the solution. So let us talk about cell here. So we'll do comparison. Remember what we need to do? We need to compare solute concentration, solvent concentration, free water molecules number, and we also need to do what? Osmotic pressure values. I think we don't need this. Yeah. So here I will write about cell, and here I will write about the solution. Here I will write about the solution, isotonic solution. Isotonic solution. So let us talk about solute concentration. Then let us talk about solvent concentration. Then let us talk about free water molecules. Let us talk about free water molecules number, and then let us talk about water potential of cell and osmotic pressure, the pi of the cell. Similarly, we will talk about the solute concentration, we will talk about the solvent concentration, we will talk about the free water molecules, then we will talk about the water potential of the solution, and finally the osmotic pressure of the solution. So see here my kids, very simple. Tell me, why are we calling this particular solution as an isotonic solution? Why? Because the solute concentration in this solution and in the surrounding environment, for example the plant cell, who is in the vicinity of this solution, who is in the surrounding of this solution, isotonic solution of plant cell. So when I am calling this particular solution as an isotonic solution, that simply means the concentration of solute will be equal in plant cell as well as in the solution. So this is what we need to start with. So the solute concentration is what, my kids? The solute concentration is equal. So cell and solution both will be at equal concentration of solute. Now if the concentration of solute is same, that means concentration of solvent will also be same, because not to forget students, for any particular solution, solvent concentration and solute concentration are relative. If the solute concentration are equal, definitely solvent concentrations will also be equal. Now tell me, if both the solutions, the plant cell and isotonic solution, will be at equal value of solute concentration, that means the free water molecules available in both of them will be equal, because the solute concentration is equal. So because the solute concentration is equal in both the cell and the solution, hence the free water molecules available in both of them will also be equal. So free water molecules equal, and you know free water molecules has a direct impact on the water potential value. If the free water molecules of the solution and of the plant cell is equal, that means water potential values are also equal. Not to forget, the pi, the osmotic pressure, is the function of the solute concentration. It is the function of the solute concentration, and yes my kids, if pi is the function of solute concentration, and you already know both the plant cell and solution are at equal solute concentration, that simply means the osmotic pressure of the cell and of the solution will be equal. And that's exactly what, and this is exactly what your NCERT writes, that in an isotonic solution, the osmotic pressure of the surrounding solution balances the osmotic pressure inside a plant cell. So that's exactly what the NCERT is trying to say when it comes to isotonic solution. So I hope students this much is pretty clear to all of you. Now let us write about the observations. Right? I hope this much is clear. Yeah. So now let us write about the observations. Quickly we'll write about the observation. Quickly we will write about the observations. So what do you observe? Simply students, whenever the solute concentration will be equal, then the water molecules that will enter from solution to plant cell and from plant cell to solution will be almost equal. So whenever, so let us discuss about the fate of the plant cell, my kids. Let us discuss about the fate of the plant cell in an isotonic solution. Whenever a plant cell is kept inside an isotonic solution, water will enter inside the cell as well as water will exit from the cell too. So there will be no net movement of water across the plant cell. So the amount of the water that will enter inside the plant cell and the amount of the water that will exit from the plant cell will almost be equal. Hence, no net movement of water will take place across the plant cell when it is placed inside an isotonic solution. I really hope, students, now this much is clear to all of you. Okay, so let me write the observation. I can also show you the image that NCERT has actually showed. NCERT has showed. Okay, it will not go now. Let it be. I really hope you are able to see this. So what is happening here? The water is entering inside as well as it is exiting, and such a cell is known as a flaccid cell. Such a cell is known as a flaccid cell. So please note, my kids, whenever a plant cell is kept inside an isotonic solution, that particular cell is known as flaccid cell, and in this flaccid cell there is no net movement of water. So what is the observation? The observation is no net movement of water, across plant cell. And please note, students, what is a flaccid cell? 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 When entry of water and entry, or you can simply write inflow of water. When inflow and outflow of water is in equilibrium, then that cell is termed as flaccid cell. So what is a flaccid cell? When inflow of water and outflow of water are in equilibrium. So you call such a plant cell as what? As a flaccid cell. So that's all, students, from this section of what will be the fate of a plant cell when it is kept in different types of solution. So when the solution is hypotonic, the plant cell will undergo plasmolysis, which is usually a reversible process. When a plant cell is kept in a hypotonic solution, it will swell up, turgid cell will be formed. When a plant cell is kept in an isotonic solution, it will become flaccid. There will be no net movement of water across the plant cells. That's all. Now let us see the last section of this class, and that is, my kids, imbibition. Yes, very important and conceptual part. Now let us learn about what exactly the imbibition means. So I'll start with the definition, and then I'll start explaining the requisites for it, and then finally the examples. So let us see what imbibition is. So see, students, imbibition is actually, first thing you need to understand, it is a special type of diffusion. It is a special case of diffusion. Imbibition is a special case of diffusion because here the water will be absorbed by solids and colloids. Yes. And when the solids and colloids, solids like dry wood, right? So whenever the solid or colloid will absorb water, there will be increase in the volume, and this increased volume right, of this solid due to the absorption of water will leads to development of a pressure known as imbibition pressure, and this imbibition pressure has or holds great importance, right. For example, if a seed is absorbing water, then due to the absorption of water inside a seed, there will be development of increase in the volume, and due to that, because of the absorption of water molecules, there will be increase in the volume, there will be development of an imbibition pressure, and this imbibition pressure will be responsible for what? For helping the seedling in coming out of the soil surface in open. And similarly, if I talk about this wood, you can see, my kids, if this dry wood is going to absorb water, what will happen? If this dry wood absorbs water, there will be increase in its size, there will be development of imbibition pressure, and you can understand the value or how huge this imbibition pressure is. So this, in the prehistoric time, the people used to use this imbibition pressure created inside this dry wood, right, after it absorbs water, to split rocks, huge rocks and boulders, right students. I hope this much is clear to all of you. What occupies the space between the cell wall and shrunken protoplasm when plasmolized cell? Obviously, very simple, Rohit, very simple. Tell me, what is a cell wall? Cell wall is actually freely permeable, right? And it is the membrane which is selectively permeable. So remember, when a plasmolized cell, in a plasmolized cell, what will happen? In a plasmolized cell, the protoplast, in a plasmolized cell, the protoplast will actually shrink and get away or shrink away from the cell wall. So there will be a space created in this portion, a space created between the protoplast and the cell wall, and here who can enter easily? Whosoever is in the surrounding can enter inside it. And remember, cell wall is freely permeable. It won't check solute and solvent. Solute and solvent both can enter. Hence, hypertonic solution will actually enter. Hypertonic solution will occupy the space between the protoplast and the cell wall. Do let me know, Rohit, if this helps. Do let me know if this helps. Chaliye. So we were talking about this. Yeah. So I have explained you what imbibition is, and also I have explained you the importance of imbibition pressure. Now let us try to summarize this on the board. So let us do this with me, students. Okay, so the very first thing that you need to understand is it is a special case of diffusion. Why it is a special case of diffusion? Because your solids and colloids are going to absorb water. It is a special case of diffusion. Next is, my kids, you need to understand is, here in imbibition, water will be absorbed. Water will be absorbed by solids and colloids, due to which there will be increase, there will be colloids, due to which there will be increase in volume, and finally creation of a pressure known as what? Known as imbibition pressure. right? And also note one very important point, students. Water will flow along the concentration gradient. Water moves along along the concentration gradient. Okay, my kids, pretty simple, right? So let me summarize this for you. What are we doing? So let me summarize this for you, my kids. What are we doing? Imbibition. It is a special case of diffusion. Why? Because here solids like this dry wood and colloids are going to absorb water. Due to absorption in water, there will be increase in this volume. Increased volume and absorption of water is going to develop imbibition pressure inside these solids or colloids, and this imbibition pressure is of great importance, right, which I will discuss in the coming few minutes. Now let us see the next point, students, that you need to understand is what is the prerequisite for imbibition to take place, right? So what is the prerequisite for imbibition to take place? First thing, what is required? There has to be a water potential gradient. What? A water potential gradient. Water potential gradient. How can you represent it in short? You can in short write delta. You can write delta psi W. Delta psi W, that means water potential gradient should exist between absorbent and liquid imbibed. And next what you need is affinity. Affinity between adsorbent and liquid. So let me throw some light on this one. Now see here, students, as I told you, what is happening in imbibition process? So see my kids, in imbibition process, water will diffuse, water will enter inside the solids or colloids, but this movement of water will be along the concentration gradient, and for water to move along the concentration gradient, so for that to take place, there has to be in advance presence of water potential gradient. For example, if this is a dry wood, for example my kids, this is what? This is a dry wood. This is what? This is a dry wood. Now you already know if a wood is dry, that means almost zero water, almost, okay. So almost zero water is present inside this wood. So whenever this wood will be exposed to the water, it will easily absorb water because of the higher or huge water potential gradient that is existing inside this wood. So hence, for the prerequisite for imbibition to take place is what? Water potential gradient between the absorbent. Who is the absorbent? Absorbent is the material that will absorb water, and the liquid imbibed. Who is the liquid imbibed? What is the liquid imbibed? Water is here the liquid imbibed. So there must be water potential gradient between the wood and the water. Next, affinity between the adsorbent and the liquid. So see students, whenever the colloids that are present inside this wood, right, this wood is made up of cells, although dead cells, but the dead cells will be made up of some kind of biomolecules. Similarly, if I talk about a seed. Seed is made up of seed coat. Inside it there is embryo, right? The seed coat, embryo, they all are made up of colloids, right? They are made up of biomolecules. So inside a structure, inside a solid, whatever hydrophilic colloids are present in them, those all hydrophilic colloids are going to absorb the water inside the solid structure. So for absorption to take place, for absorption of water to take place on these hydrophilic colloids inside the solid structures, what has to be there? There has to be affinity between the adsorbent and the liquid. What is the absorbent? It is the surface. What is absorbent, my students? It is the surface, right? On which water molecules will be, on which the water molecules will be adsorbed or adhere. It is the surface. It is the surface. So what is adsorbent? Absorbent can be a surface. It can be a surface of any hydrophilic colloid inside a solid structure, inside a seed, for example. So the water will be adsorbed or adhere on the surface of those hydrophilic colloids. So for that to take place, there has to be affinity between the adsorbent, that is the surface that is going to adsorb the water, and the liquid that is going to be imbibed, that is water. So simply, students, I can in very short terms write that imbibition is adsorption of water by hydrophilic colloids. Simple. This is also how you can define it, right? So we are done with the definition of we are done with the definition of imbibition, and we are also done with the prerequisite conditions for imbibition to take place. Now, what we should do next is, students, let us take the application of imbibition. So what is the application of imbibition? I have already explained you. Absorption of water. Water will be absorbed by water absorption. Water absorption by dry wood will lead to development of imbibition pressure, right? And this imbibition pressure, water will be absorbed by the dry wood, it will increase in size, there will be development of imbibition pressure, and this imbibition pressure can be used to split rocks, right, and boulders, right? So this imbibition is so huge that it can split the large rock. So you can understand the importance of imbibition. Similarly, the seeds will going to absorb water. Seeds will absorb water, and the imbibition pressure developed can be used, or this imbibition pressure rather helps, I should write, imbibition pressure developed helps the seedling to come out in open, right, open air. So see here, my kids, as you can see, these are the two important application of imbibition given in your NCERT. The imbibition pressure developed in the dry wood can be helped to split the rocks, and the imbibition pressure developed due to absorption of water by the seeds will help the seedlings to break the surface of the soil and come outside in the surface, right, the open one. So these are the important implication or application of the imbibition. So I really hope students this much is crystal clear to all of you. So yeah, we are done with today's class, my kids. This is all I wanted to explain in this session, students. So here let me tell you what we did. We did what is osmotic pressure, then what will be the fate of a plant cell in different types of solution, hyper, hypo and isotonic solution, and then we understood in detail what is imbibition process and what is the importance of imbibition pressure. So that's all from this class, students. I really hope everybody enjoyed this session. If there is any doubt, do let me know now, or if you still come across any question, any doubt, do let me know in the next session. So do not forget to join the next session. So that's all from this class, students. Do give me a thumbs up if you like me and this session, and do not forget to subscribe Infinity Learn by Sri Chaitanya, and do not forget to hit the bell icon so that whenever I will go live, you will be notified every time and won't miss any single session in future. That's all, students. Thank you very much for joining this class.